In this video, we are going to study a magnetic magnetic effect of electric current. So we know that an electric current carrying wire behaves like a magnet. See, if uh, in a wire electric current is flowing, it will behave like magnet. How do we know this? Because a compass needle is deflected on passing an electric current through a metallic conductor. When a compass is put nearby a current flowing conductor, then the needle of the compass get deflected. So so that we know that it has some magnetic properties also. That is why the needle is deflecting. So thus we can say that electricity and magnetism are linked to each other. And then what about the reverse possibility of an electric effect of moving magnets? So we are saying that in a conductor, when electricity in a conducting wire, when electricity is flowing, it produces a magnetic effect around it. So let's reverse this. Let's we have a conductor, conductor who doesn't have a flow of electricity. We put a magnet around it. So what will did if the current uh, conducting if the metal conducting current causing a magnetic effect, then the magnet can cause a electric effect, in this case of vice versa. So in a wire in which no electricity is flowing, and the magnetic magnetism around it, magnets around it, can create electricity in it. So the electricity and magnetism are linked to each other, and they are reversible. Let's talk about magnetic field lines, magnetic field and magnetic field lines. Magnetic field line looks like this. It goes from the north to the south, and this was the experiment in iron filing near the bar magnet aligned themselves with the field lines. A region surrounding a magnet which is in which the force of magnet can be detected is said to be magnetic field. So magnetic field is like the region around a magnet in which the force of the magnet can be detected. About its jurisdiction, it talks about jurisdiction, and the line in which the iron filing align themselves in respect of the magnetic field is called field lines. These are called field lines. You can see the field lines are lying from north to south. So these are the field lines. An effect of the magnetic field uh, on the iron filing, this the range will be called is magnetic field. So the magnetic field line goes from the north to south. A magnetic field is a quantity that has both direction and magnitude. And field lines emerge from the north, and it merges to the south. Inside the magnetic bar, the direction of the field line is from the south pole to north pole, is from south to north inside the bar, and thus the magnetic field lines are closed curves. So these are closed curves. A relative strength of the magnetic field shows the degree of the closeness of the field line. Greater, greater where the field lines crowded, greater where the field lines are crowded. So if the field lines are closer, and it shows the magnitude of the magnetic field strength, more will be the strength of the magnetic field. Magnetic field due to a current carrying conductor. Let's talk about uh, current carrying conductor creates magnetic field. We discussed above that deflection of needle happens in opposite when the direction of the current reverse, in which like we did an experiment where we put a compass here and we flow electricity like this, and in another circuit we flow electricity in opposite direction. So what happened, what we observed, the compass needle changed in opposite side. So we uh, can know about the direction of the magnetic field, in which direction of the magnetic field. So we have a one rule for it, which is called right hand thumb rule. In fact, if the current is increased, the deflection also increase. This indicates that the magnitude of the magnetic field produced as a given point increases as the current through the wire increases. So so about the direction of the magnetic field, suppose we have a right hand thumb rule. When our thumb is up and the thumb's direction of the thumb shows direction of the current, and the direction of our fingers, our finger shows the direction of the magnetic field. So a pattern of concentric circles indicating the field lines of the magnetic field around the straight line conducting wire across the circle show the direction of the magnetic field lines. uh, this is right hand thumb rule. And in second in this one, then second picture, closed a close up of the pattern obtained. This patterns obtained when electric current is being flowed in this metallic wire. The magnetic there's a magnetic field forms. There's a magnetic field produced by a given current in a conductor decreases as a distance from it increases. So suppose this is a current carrying wire, and the magnetic field line here will be high density and it will decrease slowly. Let's talk about the right hand thumb rule. This is the right hand thumb rule. This is the direction of the current, and the direction of your fingers will be direction of the magnetic field. When your finger then your fingers will wrap around the conductor in the direction of the field lines of the magnetic field. See, thumb direction will be the direction of current, and your fingers, the rest fingers direction will be the direction of the magnetic field. Let's talk about the electric field due to the current through circular loop. We studied about here a straight current. Let's talk about a circular loop. By the time we reach these are the magnetic field lines produced by a current carrying a circular loop. It looks like this. This is what happening, and the center in the field lines which is passing to center of the circle are straight. By the time we reach at the center of a circular loop, the arc of the big sized circle would appear as a straight lines. Every point on the wire carrying conductor would give rise a magnetic field appearing as a straight line at the center of the loop. So we know that if a conductor carries here, the magnetic field line will be this. Just imagine and bend this. It will be like again this. And this is what happening here in this case. And also as we go far, the magnetic field lines will become weak, and in center it is like getting affected from the all sides. So that is why the failed lines which are passing through the center are almost straight. By applying the right hand rule, it is easy to check that every section of the wire contributes to the magnetic field lines in the same direction within the loop. And this rule is also called Maxwell rule. Which rule? This one, the star pointed. Right hand thumb rule is also known as Maxwell Crookes rule. Let's talk about the current field lines due to uh, due to the current in the solenoid. So solenoid is a wire which is like wired like this, and we will pass current in it. The field line inside the solenoid are in the form of parallel lines, and this indicates that the magnetic field is the same at all points inside the solenoid. So there is a high density parallel lines inside a solenoid, and inside the uniform field lines are uniform, and the strong magnetic field produced inside the solenoid can be used as a magnetize a piece of magnetic material like a soft iron. When placed inside a coil, then the magnet so formed are called electromagnets. So this is how the field lines is appearing in a current carrying solenoid. These are very dense and uniform and parallel inside a solenoid, and it forms this circle like structure, and the density the density will decreases as we go away from the solenoid. And this inside high uniform and high intensity magnetic field can be used to magnetize any material, any magnetic material, and these magnetized materials are called electromagnets. Field lines of the magnetic field through and around the current carrying a solenoid. Okay, when a current carrying a solenoid is used to magnetize a steel rod inside it, an electromagnet. So we have put a rod in it. You can see here a electric rod, iron rod is here, and when we place it, it magnetizes this electric rod, and it also gains the magnetic properties. It also gains the north and south pole and all that. Let's talk about the force on a current carrying conductor in a magnetism in magnetic field. So we have learned that the electric current flowing through a conductor produces a magnetic field, and the magnetic field produced exerts a force on a magnet. The field the field so ex- so f- the field so produced exerts a force on magnet placed in the vicinity of a conductor. A French scientist Henri Marie Ampere suggested that the magnet must also exert equal and opposite force on the current carrying conductor. So both the magnet and the current, so both the magnet and current carrying conductor exerts equal and opposite force into each other, and it shows that the direction of a force on the conductor depends upon the direction of the current and the direction of the magnetic field. Definitely force is depending upon the direction of the field and current, and this is like calculated. This is like uh, you know uh, force can be known by this Fleming left hand rule, and these all the forces and field lines and currents are mutually perpendicular to each other. That means they each they with each other will form a 90-degree angle, and thumb will point in the direction of the motion or the force acting on the conductor. So suppose here, here in the Fleming left hand rule, if this middle finger shows the direction of the current, and the indicator shows index shows field lines, magnetic field direction, and the thumb shows the force on it. Magnetism is in medicine. We know that MRI machines are based on this magnetic properties, and an electric current always produces a magnetic field. Even a weak iron current that travels along the nerve cell of our body produces a magnetic field. And when we touch something, our nerve carrying electricity impulses to the muscles. Our nerve cell carry a electric impulses to the muscles. We need to use them. This impulse produced is a temporary magnetic field. Even our body is also having a magnetic, produces magnetic field, because in the nerve systems have, they have a messaging system, and it is based on the electric impulses, and this small electric impulses also have a small electric, field, a temporary magnetic field. As long as the impulse is there, electric impulse, a temporary magnetic field is there. These fields are very weak and about 1 billionth of the earth magnetic field. They are very big, almost negligible. And two main organs in our body where the magnetic field produced is a significant, which is heart and brain. So these are the organs which have a significant magnetic field, heart and brain. The magnetic field inside the body forms the basis of obtaining the image from the different parts. This is done. This is done using a technique called magnetic resonance imaging. Analysis of these images helps in medical diagnosis. Magnetism has thus got importance in medical use. Let's talk about the electric motor. What it does? It converts the electrical energy to the mechanical energy. And this is a working of the electric motor. How when we pass electricity here in this wire by a battery, this coil will rotate, and the electric current then is converted into the mechanical rotation. This mechanical energy is created. So this is how the electric motor works. We'll not go into detailed working of that. Then let's talk about the electromagnetic inductions. How a magnet can be used to produce electricity. We have already studied that the current carrying conductor is placed in a magnetic field such that the direction of the current is perpendicular to the direction of the magnetic fields. So magnetic field lines are always, perpendicular with the direction of current, and it experiences a force. Then this force causes a conductor to move. Now let us imagine a situation in which the current is moving inside a magnetic field, or a magnetic field is changing around a fixed conductor. So it was an important breakthrough, and in discovering how the moving magnet can be used to generate electric current. A moving a magnet towards a coil. This is solenoid. Set up an current in the coil circuit, as indicated by the definition. by the deflection in the galvanometer needle. This galvanometer is a device instrument that detects the presence of the electric current. So what we doing it, we are making a solenoid, this solenoid, and we are connecting the solenoid ends with a galvanometer, which will detect a presence of a current, if any. So when we move a magnet in a solenoid like this, to and fro, we'll move it. Changing magnetic field will constant magnetic field will doesn't have any effect. Will magnetic field will change. This is we can move manually this magnetic bar. What we seen that the galvanometer this needle deflects, and this shows that this moving magnetic field, changing magnetic field and moving electric bar can be used to produce a electric current. When a coil and the magnets are both stationary, there is no deflection in galvanometer. Thus, it is clear from the activity that the motion of the magnet with respect to the coil produces induced potential difference. It is creating induced potential difference. When there will be potential difference, we set up an induced electric current in a circuit. So when there will be a potential difference, there will be an electric current that we have studied in earlier classes. And it was a Michael Faraday who did the significant thing, working with this magnetism, and he was a experimental physicist. Discoveries include electromagnetic inductions he discovered and law of electrolysis. This is another example. So when we do this experiment, we have two circuits here. One is connected with a galvanometer, which detects the presence of electricity, and second is a circuit, a complete circuit connected with the battery, and we are currently turning on and off this circuit, currently changing the current in this circuit. That means currently changing the potential difference. So what is doing, it's changing current is also changing the magnetic field. Okay, and this travels here, this changing magnetic field travels here, and this changing magnetic field is also producing here a in induced, is inducing a potential difference, and these potential differences also is making a current flow in this second wire, in second circuit. Here we are calling a coil it, first coil and second coil. This process by which the changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. This is called electromagnetic induction, and in practice we can induce a current in a coil either by moving a magnetic field or by changing the magnetic field around it. So there must be a relative movement between these two things, wire, either in a wire solenoid or in a magnetic field. If there is a relative movement between them, the current will be induced. Why current get induced? Because it induces potential difference. The induced current is found to be the highest when the direction of the motion of the coil is at right angle to the magnetic field. When the relative motion of the magnetic field and coil is 90 degree, suppose if the magnetic is this, suppose a solenoid, this solenoid, and we move through this. These lines are this way, the current lines are this way, and we are changing doing the magnet this way. So when their relative motions are parallel to each other, then the induced current will be the highest, and will reduce slowly as we decrease or increase the angle. If the forefinger indicates the direction of the magnetic field, this forefinger, direction of the magnetic field, the thumb shows the direction of the motion. This shows the direction of the motion, and the middle finger will show the direction of the induced current. Based on this electromagnetic induction, we have one more application here. Like, this is based on the electromagnetic induction, and it is used to generate electric current. The mechanical energy is used to rotate a conductor in a magnetic field and to produce electricity. We learn in a motor when electric current is used to produce mechanical energy. Here the mechanical energy is used to produce electrical energy. So mechanical energy is used to rotate a conductor in a magnetic field to produce electricity. So the mechanical energy is converting into electrical energy. Here we are not in here we are in, like, when we study a motor, there was here a battery, which was making the potential difference and flowing through the circuit. But in this case we have a galvanometer which will detect whether we got a current or not. When we mechanically rotate these blades in the magnetic field, its magnetic field changing magnetic field, then this will produce this not changing magnetic field, but there is a relative motion. When there will be relative motion between magnetic field and conducting wires, it will produce induce a current. And to get this gets this produces a direct current. To get a direct current, a DC which does not change the direction and time, so this generator produces direct current. And this is a unidirectional current is produced. The generator is called DC generator. So these are called DC generator because they produces DC generator. The difference between the direct current and alternating current is that the direction that the direct current always flow in one direction, whereas the alternative current reserves its direction, reverse its direction periodically. And this is what is alternative. This way is mapped like this. This is what direct current is, DC, and AC is this. It reverses its direction like a wave. And most power station constructed these days produce a AC. In India, the AC changes direction in every 1/100 second. That is, the frequency of the AC is 50 Hertz. And important advantage of AC over DC is that electric current can be transmitted over long distances without much loss of energy. So AC is used. Why? Because it get less lost in long distances transmission. So when AC is a 50 Hertz, this means in a 1 second light bulb glows 50 times and did not glow 50 times. So it is changing its direction 100 times in a 1 second. So this is how it will represent it. This is suppose a 1 second time, and this will change the direction 100 times in a 1 second. And we know that one complete circle will make a 1 hertz, 1 frequency. This complete this is a one complete frequency, and this is again one more. So it is changing direction two times, one is up, one is down, and it's so that is why when it is changing direction 100 times, its frequency is getting 50, because one complete cycles when it covers, this is called 1 of hertz. So what will happen when it is changing the direction 100 times? 50 times it will glow, which is 15 numbers, 50 uh, positive will be, and here the 50 time it will not glow. Let's talk about the domestic electric circuit. And we receive supply of the electric power through a main supply, which is called mains, and one wire in this supply, usually the red insulation cover, is called live wire. So red wire, the wire which is red, in red insulation is rubber. This is material which insulates kind of isolate the current, and these are non-conductors. They are bad conductors, like, because they have a high resistance. So the live wire which contains current, which brings current in our homes, are in red color, and they are called live wire. Another wire which is a black insulation, which is a black color, are called neutral wire or negative. This does not have electricity, and so when we receive it in our homes, and in our country, a potential difference between these two wire is a 120 volt. So this is a red wire, it's coming to our switch, and let me draw with this, and this is a switch here, 1 2 3. Red wire will come, and the black wire will go this way. So the potential difference between these two wires is 2 to 220 volt. So this potential difference, this 220 volts of potential difference, makes the current flow, and this live wire, when we connect a plug, a heater, something else, the current flows through these things, a resistor and a bulb like this, and so the current comes in our home through red wire, and then comes from red wire and travels through resistance, our electric appliances, and then it goes back through the black wire. We have one more socket, let's discuss about it. Often two separate circuits are used, one with 15 ampere current rating for appliance with a higher power rating, such as geysers and air coolers, etc., and another circuit of the 5 ampere current rating for bulbs and fans and all that. So there are two separate circuits, one for the higher power consuming electric gadgets, one is for the low power consuming. 15 volt is 15 ampere for higher, and 5 ampere for the lower. There is an earth wire which has an insulation of green color, is usually connected in a metal plate deep in the earth near the house. It is used to save. It is used as a safety measure, especially those appliances that have a metallic body. For example, electric press, toaster, these things. The metallic body is connected to the earth wire, which provides a low resistance conducting path for the current, and thus it ensured that any leakage of current in a metallic body of the appliance keeps its potential to that of earth, and the user may not go to severe shock. So what he's saying is, we have another green wire which is goes out of earth inside the ground. Earth is this. So what is that? Suppose we have here a electric heater. Okay, so electric heater, what will do, it will pass the electricity from a high resistive material. So what will happen, the electricity, that it will resist, will be converted into light and heat, and sometime there can be some leakage, and all the metallic body around it can have a significant potential difference, and when we usually touch it, we may get a severe shock. So to make it safe, useful, we have connected uh, the outer metallic body with another wire which is called earthing wire here, and it has a low resistive material, made of a low resistive metal, so it will easily flows the excess the current which is coming in the metallic body to the earth. So it maintains the potential difference between this and this. Earth and this is the same, so we do not get a severe shock. We get a shock, but that will be very small, it will not be severe. So this is a preventive measure. So this is what we have explained. See a live wire coming in our home. Thus first there is an electric fuse. When the voltage will be high, and the wire will automatically melt down, and there will be no conduction of electricity. It is again safety measures. And then it goes, then the meter, it records, measures the flow of electricity, in kilowatt, 1 watt, 2 watt, and this is why we get our electric bills. And this is a distribution blocks. Well, we are distributing into multiple circuits. We have just discussed, we have two types of circuits, which is for one for 15 ampere, one for 15 amp, and one for 5 amp. 15 amp for heavy loaded, heavy electricity required appliances. This is for the low, small bulb charging phones and all that. And this is circuit, the red wires carrying, this is circuit, and again it's the black wire, electricity coming from the red one, it passes through our appliances, and then it's flow banks through the black wire. And earth wires is connected with the metallic covering of our appliances. If in case of any leak, or it safely conducts electricity from this metallic covering to the earth. Fuse in a circuit prevents damage to the appliances and the circuit due to the overloading. Overloading can occur when the live wire and the neutral wire come to the direct contact. There will be the overloading or electric fuse when the live and the black wire comes together without passing through, without connecting through any resistance, any bulb or any heater or any something. It will, if we directly connect, there will be the overloading, and there will be fuse. And in such situation, the current in the supply abruptly increases. Definitely the current will abruptly increase, and this is called short circuiting. And overloading can also occur due to the accidental hike in the supply of the voltage. It can be due to the accidental hype in the supply of the voltage. Suppose the voltage is 220 in our home, suppose it becomes 500 voltage, so definitely there will be the high voltage, and our, these appliances will this electric gadgets will get fused or damaged, will get damaged, and the fuse prevents it to break down the high voltage, uh, you know carrying electricity by melting the wire. Sometimes overloading causes caused by the connecting too many appliances in a single socket. This is also important thing. If you apply it, if you trying to charge or consume you know electricity by connecting too many appliances in a single socket, this will also create overloading. So let's quickly revise the chapter. We have almost completed it.